again, this is only the fifth week, second day, and today we'll have midterm three. You must start the test before 8 p.m. All right. Okay. Any questions before I start section 3.9? No questions? Okay, then let's start section 3.9 then. So let me save this page and then clear. Wait, did I share a file? Oh yeah, okay, files. So am I sharing this page? Am I sharing this page? Now I'm sharing this page. There we go. Okay, so section 3.9. Now the section 3.9, the topic is antiderivatives and indefinite intervals. It sounds like two topics, but the two terms are actually almost the same. There's a difference between the two terms. Again, antiderivatives and indefinite intervals. Is there a difference? And yes, there's a slight difference, but you know what? But the two terms are roughly the same thing. They're roughly the same thing. And by the way, one is antiderivative. It's kind of related to derivatives, which we have been studying on this chapter. And then the other name is indefinite intervals, and as you can see, it's an integral. So which is actually the other topic. The two topics. On calculus 1, we have basically limits, and we have derivatives, and we have integrals. So the main two topics are actually derivatives and integrals. And integrals is the reverse procedure of derivatives. So, which is the main topic of chapter 4. Now, section 3.9 is like a bridge section. It's like a link between chapter 3 and chapter 4. This section, this topic, antiderivative and indefinite intervals, could have belonged to chapter 4 as well. In some calculus textbook, this topic is at the end of the derivative chapter, or sometimes this topic is at the beginning of the integrals. So again, this section, this topic can be part of derivative chapter, or it can be the beginning of integral chapter. Okay, so again, it's like a bridge. Okay, so in our case, I have decided to put this 3.9 together with chapter 4. So on this test, this section is not covered, of course, on today's test, but it will be covered as part of chapter 4 on the next test. Okay. And section 3.8, those of you who wonder, the topic was Newton's method, and that method I am skipping, okay, due to time, and also none of the future section is going to depend on section 3.8. So section 3.8 has no dependency. Okay, that is no other sections. Those sections later will depend on section 3.8. That is Newton's method. So hopefully we'll be okay. So I guess I'm going to put the burden on you to study Newton's method. Okay, for those of you who need that Newton's method later in a later course. And by the way, it is actually a very simple section. It is a section which all of you can manage to study on your own. Okay, it's not too hard, but again, that would cost me a lot more than 30-40 minutes or so. So I think it's better for me to spend time on these main topics. Okay, so let's look at it. Section 3.9 antiderivative.
What were you saying?
Did you put stevia in?
Yeah.
What is section 3.9? Okay, so the section 3.9 is basically this right here. It's the opposite derivative. So basically, let's say, for example, if you have, let's say we have let's say we have x to the fifth power. Then we have x to the fifth power here. X to the fifth power. Now we want to take the derivative with respect to x to the fifth power. So let's say d dx. The d dx is what? The d dx of x to the fifth power. What is that equal to? That is equal to what? 5x to the fourth power. So d dx is the derivative. That's the derivative notation. Okay. By the way, the d dx itself is not any function. This d dx right here. This is part of this is derivative of something. And in this case, it means if you have x to the fifth power here, that means this is now the derivative of x to the fifth power. And that of course, we know that is f5 times x to the fourth power. Now, we have the opposite procedure. So we have the opposite procedure, and that is this. So how about if you now have 5x to the fourth power? 5x to the fourth power. And we integrate this. This is the sign of this is the sign of an integral sign. And this is dx. Then we put dx here. If you put this on here, this is now called the antiderivative. Antiderivative, or it's called the indefinite integral. So this is read as the antiderivative of 5x to the fourth power, or we say the indefinite integral of 5x to the fourth power. And what is it equal to? That will come out to be, what? That will come out to be, let me write it.
What is it?
Now, of course, we go back to
Yeah, if you're going to talk, we like doing the
which is
one.
x to the fifth power.
I have no more on these.
By the way, x to
So,
the fifth power is not
and
the
the emergency.
derivative is the 5x to the fourth. So we actually put it plus c here. Plus c. And that c is any constant. C is what? C is any constant. So let me write that down. That is what? That is any constant. C for constant is actually any constant. Any constant. Constant is a fixed number, but in this case, c can be any number, but it's not a variable. Unknown constant is not the same as a variable. Okay? So there's some similarities. They're both unknown, but constant is a number which you assume it is fixed. It's not changing, but we don't know what that is. Okay? So that's a constant.
Can the constant be 0?
Yeah, the constant can be 0. Yes. Now, first, let me maybe I want to make some comments about this. So when
This is
we
interesting,
write the
Liam.
expression x to the fifth power plus
This is really
c,
boring.
let me see. So when we write x, let me write this in maybe black. If we write this x, when you write an expression like this, x to the fifth power plus c, what that means is this is referring to a family. So when you say x to the fifth power plus c, that really means x to the fifth power, the c could be 0, or it could be x to the fifth power, and then what x could be? It could be x to the fifth power of the plus 1. The constant could be 1, or the constant could be 0. In fact, the constant could be any constant. It could be x to the fifth power, and then what? Minus 1 over the 2, and then the list goes on. In other words, the c can be any number. And then if you pick any of these functions here, if you take the derivative, of course, being a 5x to the fourth power, that's because the derivative of the constant is 0. And then the list goes on. So when we write a question such as this, with an unknown constant like this, what we really mean is this is referring to not a single function. So therefore, this guy right here is not a single function. It's not a single function. Not a single function. Not a single function. Basically, this is referring to how a family of curves. Family of equations. Family of expressions. Let me call this family of functions. So it is not referring to one function. So when you write x to the 5 plus c, we are not referring to one function. We are actually referring to a family of functions. Again, it is referring to family of functions, not just one single family. Okay? And sometimes we call them family functions. We actually sometimes we call this general function. A general function. A general function meaning it is referring to a group of functions or a family of functions. So in this case, what we're saying is, so when you say antiderivative of 5x to the fourth power, yes, we do that correct. Then what is the function which 5x to the fourth, and that is x to the fifth power. And then x to the fifth power is not the only function whose derivative is 5x to the fourth power. That function could be x to the fifth power, but also x to the fifth plus 1, or it could be x to the fifth minus 1 over square root of 2. It could be x to the fifth power plus, and then any constant, positive or negative. And so we have a whole group of functions here, and that's what this x to the fifth power plus c is referring to. So, like in this class, this c is called the constant of intuition. It's not a big deal, but this c will actually play a major role in those math classes which some of you will be taking, such as if you take, let's say, math 15, a differential equation, then you will have this c will have a major role. In this class, you don't have a major role, but at least you need to understand what this c is. Okay, in this case, it's anything. Okay, so now let's move on here. So now section 349. Let's come back here, and let's see. Let's start from this theorem right here. This theorem right here, of course, is the corollary to mean driver theorem. This theorem was showed up in section 3.1. In this part, I'm writing this again. So what was the theorem here? This is by the way, this is part A. I also moved it to part A. So what is the problem? If f prime of x equals 0 for all x, then f of x is a constant. So if you have a function whose derivative is 0 all the time, so we have a function whose derivative is 0 all the time, then what is that equal to? Then the function must be a constant. It kind of makes sense. So what we are really saying is this. What we're saying is, yes. So if you have, let's say, f prime, so if f of x, equals a constant, if f of x equals, let me write, how about this? Maybe I'll just cut this in. Okay, so basically, the thing is this. Let me call this an example. Is this. So basically, what we're going to do is if f prime, of x equals, let's say, 0, if f of x, if f of x is equal to c is a constant, f of x is a constant, then the question is, does this imply that f prime is 0? Yeah, this is no. If f prime of this, the comma is confusing us, so let me remind you. So now, if f of x equals c, if f of x equals a constant, then from there, can you conclude that this derivative? Yes. This is called differentiation. This is called the differentiation. This is what if I take the derivative. But now the reverse question is this: if f prime of x is equal to 0, then the question is, can it conclude that f of x is a constant? That's the question mark. Can you conclude this? And of course, this is not an obvious question. It is not automatically yes. If f of x is a constant like 2 or 3 or any number, then the derivative is 0. But what happens if you have a function whose derivative is 0 every time? If derivative all the time, that means f prime of x, in this case, is what? F prime of x is equal to 0 for all x, not some x. It is actually referring to the 0 function. If f prime of x is the 0 function, that is, f prime of x is 0 for all x, then can we conclude that f of x is a constant function? That is, f of x is constant. Can you do that? Yes, we can. And that's what this section is all about. If you have a function whose derivative is 0 all the time, then f of x equals what? Is a constant. If we can say that. Now, in a similar way, part B is the same. It's very similar. Part B can be proven easily by using part A, by the way. Okay, so now what is part A? Part A is this. If you have two functions whose derivatives are the same, if the two functions have the same derivative,
Darling.
Can only differ by a constant. Okay? But their difference cannot be something weird. Okay? If two functions have the same derivative, then that means the two functions can only differ by a constant. Okay? And if you want to, let me give you proof of this part B here. So let me give you the hint for part 2. Basically, what this means is the part B is basically this. We have what is the proof? The proof, let me just put on the left margin here. Basically, if f prime is equal to g prime, we have this. Then what does that imply? That implies that f minus g and f prime is equal to 0. Equal to 0 for all x. And equal to 0 for x for all x. Just like this. You know what? Maybe not like this. Right? Okay, so how about this? Let me write it stating. If f of x equals g prime x for all x. For all x. You know what? Like this. Okay, so let me change this to red. Okay, so if f prime of x equals g prime of x for all x, that means f minus g prime of x equals x, because we can move this f prime, we can move this g prime of x to the left hand side, and you can see that one of the differentiation rules we have is that f minus g. So what is f minus g prime? F minus g prime, let's write this here. F minus g prime is equal to f prime, and then what? Minus g prime. So basically, we are applying the differentiation rule. So if we bring this g of x to this side, then that will be f prime of x minus g prime of x. And then f prime of x minus g prime of x can be written as f minus g of x, and then the whole thing prime. And then once we have a function whose derivative is 0 all the time, what can it conclude? Now what? Use part 1. Now what is it? By part A. By part A, what can it conclude? We can now
He's going in there. He's going in.
that f of x. We can now conclude that f of x and then minus g of x is actually equal to constant. And so anyway, on the left part here, that is actually a proof of part B. And make sure that you know all these things here. And even the theorems and formulas, which I did not prove, I think they are good source of study, good source of material I want you to study. Because all these techniques which you see in the proof, they're actually something common in problem solving. And they involve problem solving skills. So all the proofs you see here is worthwhile. Okay? To study. Okay, so part B says again, if the two functions have the same derivative, then the two functions may not be the same function, but the two functions can only differ by a constant. That kind of makes sense when you look at the graphs. Yeah. So I can, if you go to a graphic calculator, you can see if you see two graphs of functions who differ by a constant, then they're either what? Then one graph is a translation of the other graph vertically only. So if you move the entire graph up or down, then that's what we mean by adding a constant. And then if you know at any point x, if you look at the tangent line, the slope, the tangent line, that is the tangent line to all be parallel at the same x value. And so it's not hard to see that. Okay, so now definition. Definition here, now let's look at the definition here. The definition is this. The definition. Definition right here. If function f is an antiderivative, so what do you mean by antiderivative? So a function f is an antiderivative of f. We say capital F is an antiderivative of function f if capital F prime is equal to small f. That's how you write it. Okay? Capital F prime is equal to small f. And now the other way of writing is, of course, writing it this way. writing this guy right here, we actually mean the same thing. Again, capital F is the antiderivative of small f. Oh, wait, did I say this right? Yes. Capital F is the antiderivative of small f. That means small f, capital F is the antiderivative of small f. That means the derivative of f is small f. So the derivative of small f is the derivative of capital F is small f. The antiderivative of small f is capital F. So again, antiderivative simply means it is the reversal derivative. So the notation is this. Capital F, the indefinite interval of f of x dx is equal to capital F of x dx. And this is true. This if and only is right here. This means, so what does that mean? What does that arrow, the double arrow mean? The double arrow means. That's what it means. Okay? So just a reminder, that double arrow means. That's what it means. So that means capital F comes into the small f. Now once again, here let me tell you the difference between the term antiderivative and the indefinite interval. And the difference is that, the antiderivative, it is actually referring to each of these functions. They are called the antiderivatives, each of these derivatives. But what does indefinite interval mean? Indefinite interval usually means the entire family of functions. So when you refer to the entire family, we say indefinite intervals. The individual member functions here, individual functions, we call them antiderivatives. And as we see, there is not much of a difference. Okay? It's like this. It's like this, as you know, my last name is Lee, and so I'm part of the Lee family. And somebody, let's say, gives me a phone and calls us, and then asks us, can I talk to Mr. Lee? Well, Mr. Lee, let's say Lee is a family name, but if they say Mr. Lee, well, that could be me, but I have a son too. I have sons, and my sons, they're also Mr. Lee as well. So when they say Mr. Lee, are they referring to me, or are they referring to my son? Who are they referring to? So that's the issue here. But again, whether the Lee is there or Mr. Lee, of course, if you somebody says Mr. Lee, it's probably like it's referred to me. It could refer to the individual, or it could refer to the entire family. Okay, so that's the difference. So the difference between the indefinite interval and the term antiderivative is not that significant at this point, although there are some differences there. Again, this is the difference. Antiderivative is usually referring to each function, whereas the indefinite interval is referring to the entire family. But again, the difference in meaning is not so significant. Hence, in this class, we are just going to use the term interchangeably. So if you look at the title, antiderivative and indefinite intervals, well, I should have put an antiderivative with an S there, and then indefinite intervals. It sounds like we have two topics to study, but this is not two topics. This is just one topic. We just have two different names. In many calculus textbooks, they just call the section antiderivative, or some books they just call it anti-indefinite intervals. So they don't put a title like this. But again, whether they title like one name or two names is the same thing. Again, the two terms, they mean roughly the same thing. Okay. So now let's get to example 1. So example 1. Let f of x equals x to the 4th power. Find all functions f of x such that capital F prime is equal to small f. So here, they're not asking us to find f prime, small f prime, but they're asking us to find the function whose derivative is f of x. So once again, here the question is not to find the derivative of small f, but to find the function whose derivative is small f. So how do you write this? So find all functions f from x to small f. So what's the antiderivative, or what's the indefinite interval of x to the 4th power? And that will be the solution here. I can write it out. So the solution here is going to be what? The solution is going to be capital F of x. So we start with the f of x. So what is f of x? F of x is equal to now capital F of x equals small f. And all of the way of writing this guy is writing it this way. Integral now this is referring to the antiderivative or the antiderivative or the antiderivative or the indefinite interval small n. So capital F is a function whose derivative is small n. So again, this right here and this right here, they basically the same thing. And now what is this equal to? This is equal to now integral and then x to the 4th power. Oh, I did this already. Did I do this already? I kind of did it, didn't I? Oh, yeah, it was similar. So now the question is, what are the functions whose derivative is x to the 4th power? And this is x to the 4th power, so we know that if we add an x1 to the x1 and then we get x to the 5th power, so what is the derivative of x to the 5th power? The derivative of x to the 5th power is what? Is what? Is
5x to the power.
Yeah, so we need to put 1 or 5, right? That's right. We need to put this guy and then 1 of x to the 5th power, and then now, then how much the constant? Yeah, we can have any constant. This constant could be 0 or 1 or 2 or any number. And so we have a whole
Good job,
family
man.
of functions whose derivative is capital F, whose derivative is small x to the 4th power, whose derivative is x to the 4th power, but all the difference is only a constant. So that's what part B is. So the final answer is this guy. So capital F of x is the whole family of functions, which is what? 1/5 x, 1/5 times x to the 5th power plus c. And now let's look at example 2. Find all functions f such that capital F small f prime is equal to sin x. So now what are the functions whose derivative is sin x? Okay, tell me what the function f is going to be. So if you have a function here, you can create a chart, yeah? Let's create f prime. You create a chart, let's see what we have. So here what we're saying is that this f is what? This is sin x. So this is sin x. What could the function be? Now we know that if this guy is, how about this? So here, let me see, this one here, if you call this guy g, then this will be an antiderivative. Basically, we call it this way. So if now we know that if the function is cosine x, then the function is cosine x, then the derivative is what? Minus sin x. You know that. If the function is cosine x, then the derivative of cosine x is minus sin x. But what we now have is sin x, not minus sin x. So what we only need to do is multiply by negative here, and we now get what? Minus cosine x. So if we take the derivative of minus cosine x, then we will get plus sin x. So that's what it is. So now what I'm going to do is, let me now save the screen here, and I'm going to do all this. And now I think it's time for me to go back, switch my file here to 3.9 solution file. Okay, so I can now cut out my writing. So we are now on the same function, same page, and basically this is what we have. Oh, by the way, did I write this down? Oh, I didn't write this down. You know what? I thought I added this problem, but I guess I didn't. So let me write down the properties of the properties of sigma. So here, let me write this down here. How about this? The properties of antiderivative. How about let me call this the linear properties of the linear properties. Let me just call them the linear properties of antiderivative. Two linear properties, and they are this. Because the antiderivative is the reverse of is the reverse of derivatives, it's very similar. So let me write number 1 here. So number 1, let me write this down. So rule number 1, the property number 1 is if you have an antiderivative of f plus g, then dx, this is basically equal to what? have an antiderivative with some function, then we can find the antiderivative separately and then add them up. That's what the number property is. Number two property is this. Number two property is integral. If you have a constant function, if you have a constant function, you know what? Oh, well, I'm now using the C here for constant. Then this is going to be the C times the antiderivative of f of x dx. This is a constant multiple property, and the first one is the sum property. Very similar. These two for the front. These two are the properties of antiderivative, and especially these two properties are what we call the linear properties. Linear properties. Now let me write down the other properties here. How about this? These two properties right here. How about this? How about f and then what? Plus g prime is equal to f prime and then plus what? G prime. And then we also have c times what? C times f of f prime. C times f prime is equal to c times f prime. I can look for f prime. That's f prime. Then these are the two linear properties of differentiation. The linear property of derivative. So the derivative is what we call a linear operator. And the integral is also called a linear operator. How about the many things which are linear? How about like this? How about limit? The limit of f of g, f plus g is what? Is equal to lim f, then what? Lim f, and then plus this g. And how about the limit of t times f? What is this? Of course, the limit has to exist. We have to model first about this one. So t times the limit of what? The limit of f. And of course, with any kind of limit I'm talking about. So the limit is also what we call a linear operator. So the many operations or many functions which are linear. So for those of you who will be taking more math, you will be studying more about this. And by the way, for those of you who will be taking a few semesters later, I think some of you will be taking math 13, which is linear algebra. If you are either a math major or a I don't know, math major or physics major or engineering major or maybe computer science major or some sort of mathematics major, then you will be taking math 15, math 15, which is called linear algebra. You know that course called linear algebra. The entire course is about linear operator. Okay? So this kind of a thing is the linear operator. It has two linear properties. Okay, so again, the many things which are linear. Okay, so integral is one of those linear operators. Okay, so now let's look at example one. Example one here. Let me just draw a line here. Okay, example one. Let f of x equals x to the 4th power. Find all functions capital F such that the capital F times equals small f. What do we do? Solution. Capital F is equal to small is equal to this right here, and which is equal to this right here. And so, again, this relation right here, that's the same thing as this right here. If capital F times small f, then the capital F is the antiderivative of small f. Again, if capital F, if the derivative of small f, if the derivative of capital F is equal to small f, then we say that the capital F is the antiderivative of small f. So these two are exactly the same statement. And so now, what is f of x? F of x is x to the 4th power. So what is the function of this derivative is x to the 4th power? And that's x to the 5th power. actually using this property right here. So this property or this property right here. You're applying this property. Okay? So if the derivative of x to the root, if the derivative of 5x to the 4 power is x to the 5th power, then the derivative of x to the root power will be 1 times x to the 4 power. We can always adjust by a constant multiple. That's the constant multiple property, alright, of definition. Which is one of the two major properties of definition. So now let's save this. And now save this. So now let me scroll this down. So now let's look at example, make the screen bigger. Let's look at example 2. Example 2. So for example, to find all functions f of x such that small f prime is equal to sin x. So here again the question is not to find the derivative of sin x, but we have to find the antiderivative of sin x. So now here what is the question? So now the naming of the functions is different here. Now the question is to find f of x. What is f of x? F of x is the antiderivative of is the antiderivative of f prime. So f of x equals to the antiderivative of f prime, and what f prime is given as sin x. Now what is the antiderivative of sin x? That is minus cosine x. And to find all the functions, not just one function, we put a plus c here. So this is it. So that is not the final answer. By the way, for all of these derivative problems, how do you check? Do you know how to check? How to check if your antiderivative, and antiderivative is correct. How do you check? Well, there could be many ways to check, but the standard way to check is what? The standard way to check? The standard way, you know what? Let me just not call the standard way. Let me just check. Check by taking the derivative. So taking the derivative of the answer, of the final expression of the function, answer function. Okay, so in this case, what does that mean? So in this case, we found the antiderivative is minus cosine x plus c, and so this is how we check. Okay, so we take the left hand side, we take the answer, and so what we did is minus and then cosine x and then plus c, and then take the derivative of that. So what happens if we take the derivative of that? So let's do that. So that will be what? The derivative of, that will be the derivative of minus cosine x. And then take the derivative of that. Or again, this is very simple, so you don't have to really write all these steps here. Okay? So I just know I'm writing the check for the first time, so I'm just giving you some details. And so what is that? That is equal to minus times the derivative of minus times the derivative of cosine x, and then prime, and then I can apply the constant multiple formula, and then plus, and the derivative of c is 0, and therefore what is that equal to? That is equal to minus of the derivative of cosine x is minus sin x, and so we end up getting what? We end up getting equal to sin x. Of course, you need to write any of these steps here. Yeah, the derivative of minus cosine x plus c is sin x. Okay, if you do that in one step, I'm not going to stop you. Okay, so but anyway, these are all the details. So this is how you check the derivative. You check the derivative by what? You check your antiderivative by taking the derivative in the reverse direction, of course. So get the answer for antiderivative, and take the derivative of that, and then check. Okay, and by taking the derivative of that answer function, you should get the original function. Any questions here? So now note that in this case, the final answer is the example functions. You note that in this case, if you look at the equation, if you look at example 2, it says you find all functions, not one function, but all functions. Now, did we find all the functions? Yes, we did. In fact, we found all the functions here, even though the difference is only a constant here, but nevertheless, this is actually a family of functions. So here we know that this, the final answer on here, is actually a family of functions. Family of functions meaning many functions. Although the difference is only a constant distance. Okay? The difference is not that interesting, but still, it is a family of functions. Okay, so now let's look at example 3. Example 3. Now, example 3 here is this. If you compare example 2 and example 3, there's actually not much of a difference. Well, they're quite similar. But in example 3, we now have one more condition right here. So we have what? We have one more condition. So example 2 says small f prime is sine x. F prime is not sine x. In example 3, f prime is also sine x. And the question is to find function f of x. Find function f of x is exactly the same thing. That here I go on and then I got a here, but again, and basically the same thing. In math, you have to find everybody anyway. Okay? You should always find everybody. Unless that is difficult to find. Okay, so in this case, what do we do? Well, solution. Now let's look at the solution. F of x is equal to this right here, and then so far so good. Exactly the same. So we got this answer for just like in example 2. But now this time, now these are the functions whose derivative is sine x. We got this condition correct. And this constant can be anything, any constant. But now, okay, again, no matter what this constant is, the first condition is that. But now we have a second condition. So now what do we do? Apply condition f of 0 equals 3. How do we apply the condition f of 0
She's
equals 3?
being darling.
X equals 0.
She's being adorable.
2 is function right here. X equals 0.
She's being
X
adorable.
is equal to minus cosine x plus c. Now what we do is we need that condition satisfied.
It's a small voice. Hey, what are you listening to?
And f of 0 is 3. That's where we got the 3 there.
What are you listening to?
Cosine x equals 0 there. And if cosine equals 0,
Something good?
and so what is this cosine 0? Does everybody know what cosine 0 is? What is cosine 0?
No, I'm not saying that.
0 or half? Is cosine 0 equal to 0 or is it half? Can you tell me? Is it 0 or half? What is cosine 0?
Say 1.
That's right, it's 1. Okay? So 1 here, so now I can write that step there. So I add a 1 to both sides, so we get c equals 4. So when you get this c equals 4 here, now what you get now? Plug in this c back into this guy right here. Now the c right there. Plug back in. Now the function is f of x is equal to minus cosine x plus. Now in example 3, we only have one function as an answer. So we call this one particular function. One function, or we say one particular function, as opposed to general function. General function, which could be, we could refer to a family function. So here, in example 3, the solution is one particular function rather than a family function. We have one single function. And so how do you check whether this guy is correct? Well, to check this guy is correct, you check two things. You can check the derivative. And if you check the derivative, you have f prime x sine x, yeah, that's right. And then f of 0 is 3. That's a non-calculus condition, but that is still functional. By this kind of a problem with this kind of a condition here, we have a special name for this. We call this IVT, and we call this initial value problem. Again, initial value problem, IVT, and it is a very important kind of problem when it comes to applied math. When you get to differential equations, okay? So when you take a course like differential equation chapter math 15, so math 13, I think it's math 13. It's been years that taught those courses, and I'm slowly forgetting the numbers. Anyway, you take that course, then you your job is to find all functions. For example, 2, these are all the functions with derivative. So these are all the functions. And then for example, 3, this is all the functions we have. There's only one function out there. There's only one function which is done by both functions. So we're now limited to one function. And again, this is all the functions we have. We only have one function out there which is done by two conditions. Including the initial value. We call it the initial condition. And usually the initial condition is actually
Nene, honey, remember when you woke us up in the middle of the night with truckers talking to us?
Instead of f equals 3, I could have said f of 1 or f of pi is equal to 5. Okay? F of pi is 5 or f of 1 equals 3 or something. It could be anything. But
Politicians would literally just say whatever the fuck and then not do any of it
Yep.
all the time. And we're expected to just like.
Okay, any questions here? Example. Let me take this now and now do this. Now let's now move on here. Now let's move on to example. Move on to example here. Let's see. Okay, now example 4. Find the function f of x such that f double prime of x equals 4 of x and f of 1 equals 2 and f of 2 f prime of 1 is equal to 3. So now we have a derivative condition right here. And then we have f of 1 is equal to 2.
You already asked me. I'm recording.
Now note that in this
I already
case,
said
we have a
yes,
second
okay? I give you.
So when you have a second derivative, and when you have a second, when you have an equation, second derivative of something, then after that we find the answer, we would have two constants.
Hey, Summer.
So we will have two constant of integration. By the way, this plus c we put at the end here, I should have already told you. This plus c, we call this constant of integration. So when you say integral of f, you know what? Let's just write how about this here. So let's say if you write x here, then let's say f of x squared dx. X squared dx.
Just to test that.
And then what is the antiderivative of x squared? And that will be 1/3 x cubed. If you write 1/3 x cubed like this, 1/3 x cubed, and then 1/3 x cubed and then plus c. This plus c right here, we call this the constant of integration. This constant, we call this constant of integration. We call this integration constant. Okay? So we call this the constant of integration, or we call this the integration constant. So whenever you have a derivative condition and we also take the antiderivative, then each time we take the antiderivative, we actually get a constant. We actually get a constant of integration. We get a constant. But this one has second derivative here. In this case, we have two constants. And because we have two constants, to settle those two constants, we just have two conditions. If you have two conditions at the end of these two conditions, what do you get? We will get a partial function at the end. So if you look at the variance here, we get a single function. There is no constant here because we have these two conditions. Okay, so now how do you get the solution? This is how you get the solution. Okay, so solution right here, let's see what we have. So we have this f double prime here, and so in this case, it's actually good to find the f prime first before we get to that. So if f double prime is equal to the square root of x, then what is f prime? F prime? What is f prime? F prime is the antiderivative of f double prime. So if you take the antiderivative of f double prime, you get f prime. And if you take the antiderivative of f prime, then we get f, and then we get f. Okay, so f prime is the antiderivative of f double prime, and in this case, f double prime is the square root of x. This square root of x, by the way, can be now let's see. If you have x to the n power, the x to the n power, what is the derivative of x to the n power? That will be that will be n times x to the n minus 1. Now, if you have x to the n power here, then whose derivative is x to the n power? Well, we have to reverse the procedure, and so that will be 1 over n plus 1. 1 over n plus 1 is the what? Times x to the n plus 1. That's equation to write it in times form. So the derivative of x to the n power is equal to n times x to the n minus 1 power. If you have to reverse the procedure, what is the antiderivative of x to the n power? That will be 1 over n plus 1 times x to the n plus 1. Again, if you take the derivative of this guy, then it is not hard to see that we get x to the n power. Okay? So once again, if the derivative of x to the n, if the derivative of x to the n, if the function is x to the n plus 1 power, then in this case, of course, the derivative will be n plus 1 times x to the n power. So if you do not want this n plus 1, then you have to divide both sides by over equal both sides n plus 1. So we get this one right. And by here, of course, we can have the plus c here. If we don't have actually a plus c everywhere, we can have a plus c here. And plus c, we should have a plus c actually. And then plus c could be anybody. It could be any function. Everywhere, no matter what, antiderivative, it will always have a plus c actually. Okay, so now let's have the half power. Now let's see. If the function is what? If the function is x, if the derivative is x to the half power, then what is here? Then what is the antiderivative let me tell you what the CX plus C includes. The CX plus C, what does this guy do? This guy includes what? X plus 1. Or it could include UX and then plus U. And then it includes what? 2X and then plus 2. Even though C is not arbitrary, C can be any number, this C and that C are exactly the same. Of course, CX plus D also includes 2X plus 2 as well. C could be D, but in this case, C and D are both free independently. If you look at CX plus D, if you look at this group right here, so let me this group right here. If we have this group right here, CX plus D includes this group. And then this group right here, CX plus D includes these guys right here. So note that this C and that C, although the C can be anything, this C and that C are what? They're the same guy. They're not different guys. Again, C can be any number. When you use the letters C and C, they are referring to the same C. So it does not include the like minus 28. It does include that. It does not include X plus 1. It only includes X plus 1. So this guy is 1X plus 1 and 2X plus 2 and so on. So minus 2X minus 2. And then of course I can also write a family called let's say CX and then let's say plus how about C plus 1. This is the same family as that guy? No, different family. How about this guy? How about if I write let's say CX, the CX, the CX, CX, and then a plus C. Is that the same family? Do you think that's the same family? This family right here, that's the same family as CX plus C. So that's the same family as CX plus C plus 1. Do you think they're the same family or not the same family? They're not the same family. If I write the family like this, CX plus C plus 1, then this family includes what kind of guys is this? This family includes let's say 3X and then plus 4. It includes what? It includes minus 7X and then minus 7X and then minus 6. You see this right? That's what's included here. However, X is not X plus 1 and X plus 1 is not included. X plus 10 is not included here. So these guys, this is this family. So what is this family then? What is CX plus 2? The CX plus 2C, what is it here? This includes what family is? Includes what? Includes the CX X plus 2. It includes minus 3X and then minus 6. It includes these guys. Everybody understand this? Why does the C in two different places is saying that the two C's are the same? C can be any number, but they're the same. It's like right here. If you look come to the right hand side here, and note that Note that I wrote an N here. I wrote the N. Okay, let me write this down. I wrote an N here. I wrote an N here, and we also have an N here. Now these two letters here, all the N. Now of course, you know what? When you look at this chart here, the N can be any number. But does that mean that this N and this N and this N, they must be the same? Yeah. These N's right here, they must be the same guy. Even though N can be any number, all the N's are the same number. Is that clear? if f prime is what? Is x to the negative 1. And of course, x to the negative 1, of course, is 1 over x, 1 over x, 1 over x. The question is, if the function is 1 over x, what is its antiderivative? We know the antiderivative here. No, that is the top secret, right? This you will study in chapter 6. Chapter 6. We have chapter 6 here. You actually study chapter 6. Chapter 6. Chapter 6, of course, this is chapter 6. This will actually be the very first thing you will be studying when you go to calculus. Okay? Again, study chapter 6. Yeah, chapters 1 and 2 and 3 know what we share the same calculus textbook. And if you buy a full calculus textbook, the one calculus textbook covers 3 courses. Calc 1, Calc 2, Calc 3. Okay? Of course, you can just buy a skinny book here. A thinner version is only Calc 1 or Calc 1 and 2. Okay? Good question here. Good question. David, now it's did you finish this? Did I finish example 4? No, I didn't. I did not finish example, did I? I almost finished it. I thought I did. Okay, so basically, because this is assuming an f prime is this right here, and then now f is equal to f prime, f of x is equal to the outside of f prime, so we figure this is equal to this right here. And then this time, I will talk about this letter c, right? In this case, don't call this guy by c, call this guy by d, because this is what the solution to one problem, and we have a c here, and we already settled the c, but I recommend you not to recycle the c. Is that clear? So do not go by the same name. You can call this C2, you can call this E, or you can call this whatever you want, but do not call this C. It will have a conflict with this. Again, within one problem, do not recycle the same letter. Once again, within the same problem, do not recycle the same letter. Within one problem. For different problems, of course, you can call that problem. You can call that C again. But on the same problem, do not recycle the same letter. So this guy now becomes C. So now we get this here. Now the question is, what is C? So now, what is it now? We use this condition right here. F of 1 equals 2. Plug in anything, x equals 1. Then we get F of 1 equals 2. So that's what we do there. And then we get all this. And then do some calculations here. And then we get this guy. And then final answer is this guy here. Now, how to check? To check whether you get right or wrong, what to do? You check it by taking the derivative. So taking the second derivative 2 times, then you check this guy, and then check f1 equals 2, and then check f prime 1 equals 3, and so that's how you check. Again, checking the antiderivative problems, you always check by differentiating, not by going through the procedure again. If you go back and then see whether you made any mistakes, that's what I call a procedure check. So we don't want to do a procedure check, we want to do a direct check. A direct check, by looking at this problem here, we want to check these conditions directly. In this case, we actually do the reverse. We take the derivative. To check, take the derivative. Don't interpret it. Any questions? Any questions? 9.8 meters per second squared. Sometimes they don't like numbers 9.8, so they actually approximate to 10. Then again, the 32 and 9.8, these are not exact numbers. These 32 and 9.8 are measured quantities. They're not exactly 32, by the way, alright? They're not exactly 32. Because this 32 is feet per second squared, which is feet per second per second. This is the acceleration. Then use the letter G for gravity. I call G the gravitational acceleration. It's an acceleration. So let me stay here. Let me write this down. What is G? G is equal to gravity. What is G? G is equal to gravity. The not gravity. Gravity. Gravity, this is what I call the gravitational acceleration. It's real acceleration. Okay? I want to stress that it's an acceleration. Okay, so let me maybe write this way. G is equal to the gravitational acceleration. So now let's see. In this case, we have to set up a we have to set up an axis. So now this is not going to set up an axis, but probably the most common one. What we want to do is, why don't we set up an axis? Let's say we have the Earth right here, and then let's say this is what? And then let's say this is Earth. So let me say this is Earth. So this is the Earth. Okay, how about this? This is the ground.
Can you drop an oxen?
Okay, this
What does that mean?
I will just call this the ground. Okay, so this is ground. Ground, okay, this is the ground. And then now we want to set up an axis. So let's set up the axis this way. So we need to set up an axis for the collision. So now let me write an axis this way. And now let me call this guy S. S axis. For some reason, S is a very common letter when we set up the collision axis. And then now, and then here's a mark with 1600 here. So 1600 what? 1600 feet. 1600 feet. So let me write 600 feet. So let me write 600 feet here. So 1600. Okay. So now if we set up the x-axis this way, then that will be the x plus axis. So x plus axis here. If you set up the x-axis this way, then that's the ground will be x equals 0. X equals 0 here. And over here, at the height of 1600 feet, that will be x equal to 1600.
What is that
So
noise?
we set up an axis for convenience, of course. We have to set up an axis so that we can name these positions here. So the position axis, we can set up this way. Now, this is not the only way to set up the axis. Okay? We can set up an axis like this too. We can set up an axis where this is the ground, and this is 600.
Are these your socks? Can they fit me?
Come on. Oh, those won't fit you, but the other ones will.
Which other ones?
Maybe the ones that you almost put on yesterday.
What is it? 600. So let's say this is 600, and then this is now 1600 feet above the ground, and then now what?
Whatever ones you were
I don't
missing
remember
yesterday.
this one.
They look like boy socks, not those. Not girly
And
socks.
then call this then you call this x-axis. So then basically let this guy be x equals 0, and then call this guy equal to 600. So the choice of the position axis is something we choose. It is not chosen by the problem. So if you look at example 5 here, there is no reference of axis. So the original problem has no reference of axis. So that means in order to do the problem, we have to make a reference. So we have to create an axis. We have to define an axis so that we can name these points, name this position. This is actually by far the most common way, but this is not the only way. Let's say you are in a space station, you're up there, I don't know how many miles, maybe about, I don't know, a couple
All right, darling.
miles, I don't know.
Bye.
Let's say you're up there,
Waiting.
you're very high up there, then you might want to
The
set up
rules.
the axis that way.
The rules drink on the ground.
And then where you are, you will call it x.
You have a great day.
That's what it is. Wherever you are, we will set that position we have to do. And it does not be called that, it's called that. call y, or you can call it by f of h or height. Because you can by anything here. It is a matter of how you define the axis here. I just call the x-axis the position axis s. So in this case, now solution here, let f of t equal to the height of the object t at time t after release. So here, what I've done is I've now the x-axis this way. So now I define the x-axis this way. And what is s of t? S of t is equal to the height of the object at h time t. Height of the object, that is height of the object from the ground. Okay? It's not the length of the object, but I'm talking about where the position of the object. So x of t is what I call sometimes I call this the position function. This is the this is called the
The guy got out.
Oh no, getting cooking.
position function. This is where the position function of the object. You look at this now. What we have now? In this case, now here we have these problems. Now here we have work problem. We have work from right here. Now we have to convert this into a Maxwell problem. Maxwell problem, what is it? Let's say, this is gravity. This is release. So if you release that from any height, so now the gravity will take it back. Once the object leaves your hand, what happens? Then the only force will be there. So the gravity is what? It's towards the center of the ground. Just the center here. So the gravity is actually this way. Gravity is towards the center here. So therefore, if instead of the axis this way, x plus is going that way. And now what is the gravity? Gravity is the normal time. The acceleration of the object is going to be minus g, which will be minus 32. We define this g to be 32. In this case, the actual acceleration is going to be minus 32. And this defines basically free fall. What is free fall? The free fall is basically accelerating at the rate of 32 feet per second square towards the center of the earth. That's what that's the gravity. And in this case, acceleration will be the gravity. In this case, it will be minus g because it will be towards the s minus axis. So 32 minus 32 feet per second square. If we set up the axis this way, then the acceleration will be plus 32. In this case, this axis is now down. So whether it's 32 or minus 32 depends on how you set up the axis. Now let's say the initial velocity is 0. That means that the time at 0 is 0. And then what is it? Height is 1,600 feet. That means x at 0 is 1,600 feet. So what we get is f prime of t is equal to minus 32. X prime of 0 is 0. And then f at 0 is 1,600. So let me save this right here. So now we can compare this example 5 to example 4. Example 4 and example 5. Example 4 and example 5, they kind of look alike. What do you think? Example 4 and example 5, do the two problems look alike? Mathematically speaking. Are the two problems similar? Yes. If you look at example 4, we have a function here. It's that second derivative function is given. And then we have the initial
It's
position.
more.
And we have the function position and we have the derivative position here. And if you look at example 5, we have the second derivative. Instead of f, we have f. Instead of x, we have c. But then the second derivative, we actually have the second derivative right here. This gives the constant function here. And then we have f prime, position of f prime. We have the position of f prime. S prime is the v, basically. S prime is the derivative of the function is actually the velocity. And now we're trying to come here. We run everything from the back. And so this form, this setup is actually very similar to this setup. Very similar. And so you just have to find the function s. Any questions here on example 5? There you go. Very easy. Yeah, that's right. Okay, so in chapter 1, I think I gave you the function. I gave you the position function. But in section 3.9, we now have to derive the position function. So that is the difference between example 1, chapter 1 and section 3.9. Again, in section 3.1, we derive the position function. In chapter 1, the position function was given. Chapter 3, the earlier section, the position function is given. But here, we have to find the position function. Okay, so that's let me, so this one here, this one you don't need to do. Okay, should I save it? Okay, that's okay, save this here, right? So, okay, now, if we scroll this down, then we get this example 6. Example 6 is now another free-form problem. Now, let me just go over here. Example 6, an object is really from a height of 1,800 feet at initial velocity 20 feet per second downwards. Now here, when you look at these questions here, 20 feet per second downwards, not upwards. So now we need to have the direction must be very clear. So if you set up the axis like that, and then set up like this, and we want this to be the x-axis, then what will this is the ground, we let this be x equals 0, and let this s right here be x equals what? S is equal to 1,800. 1,800 is example 6, right? In this case now, what is this? So acceleration. So in this case, this object is really, okay, 1 equals 3. The only acceleration will be the only force, which is times the relative acceleration, is what is minus 32 feet per second. Minus feet per second squared. Okay? So that will be, that is what we call free fall. Okay? Sometimes it is not a free fall. By the way, if you throw the object upwards, if you throw the object, let's say, if you throw the object, upwards, initially, is that still called free fall? knowledge